when we're doing our ACL configuration, we've got some things to keep in mind. First of all, do we need a standard or an extended ACL for our specific purpose? If we just need to match source address information, then a standard ACL might work. If we need more granular control, then maybe an extended ACL would be better. And also remember that ACLs, they can be applied in the inbound and or outbound direction on an interface, but we can only have a single ACL of a single protocol, like IP, applied in a single direction on a single interface. In other words, I couldn't have two IP ACLs applied in the inbound direction on Fast Ethernet 0/0. And to avoid filtering out traffic that we actually want to permit, it's a good idea to place more specific ACL entries near the top of the ACL, getting more general, getting more generic as we go lower in the ACL. And that's because those entries in an ACL, they're processed top down. And one of the biggest gotchas is forgetting that we've got an implicit deny any statement at the bottom of our ACLs. So if you don't permit at least one type of traffic, then everything is going to be denied. And if we're working with standard ACLs, which don't match destination addresses, Cisco recommends that we place those ACLs as close to the destination as possible, so we don't filter out traffic from that source to other destinations. Now, on the flip side of the coin, if we're working with extended ACLs, Cisco recommends that we place them as close to the source as possible. That way, we're filtering traffic out early on before it can start to consume bandwidth on our network. And finally, remember that ACLs, they're not just used to filter traffic flowing through a router. We could use ACLs to filter traffic going to a router. For example, let's say I'm trying to set up a secure shell connection to a router VTY line. We could limit that with an ACL. And other than using ACLs to permit or deny traffic, we could use ACLs to match traffic, much like we did in our NAT configuration. Remember, when we were setting up network address translation, we had an access control list used to identify, used to match inside local addresses. Now that we've taken a look at the theory and the configuration of access control lists, let's go through a few troubleshooting scenarios. Here in the first scenario, we want to prevent, with our access control list, we want to prevent traffic from PCA from reaching the servers in network 192.168.1.0/24 while permitting traffic from PCB, but the symptom is PCB is unable to reach that network. Let's take a look at our access control list configuration and see if we can figure out what is going on. We've got an access list statement saying access list 1 deny host and then the IP address of PCA. We know this is a standard access list because the access list number is in the range of 1 through 99, and we're denying the host address of PCA. So the question is, why is PCB unable to reach those servers? We're taking this access list, going into interface configuration mode for Fast Ethernet 0/0, and we're applying the access list in the inbound direction as traffic is coming into Fast Ethernet 0/0, and traffic from PCB is being blocked. You might want to pause the video right now and theorize as to why PCB is unable to reach those servers. And when you think you know what's going on, you can resume the video and we'll talk about a solution. As you were thinking about this, I hope you remembered that there is an implicit deny any at the bottom of our access lists. So if I do not explicitly give permission for PCB to reach the 192.168.1.0/24 network, it's not going to be allowed. And here we don't have any permit statements, so we're not going to be allowing any traffic to flow through the router over to the servers on the right. Let's take a look at a second scenario. And this scenario has exactly the same goal and the same symptom. PCA should not be able to reach the servers and PCB should be able to reach the servers, but the same symptom we had last time, PCB still is unable to reach the 192.168.1.0/24 network. Let's see if the configuration is any different from last time. Here we've got an access list number 2, so it's still a standard access list, and we're denying 10.1.1.0, which is the subnet including PCs A and B, and we're giving a wildcard mask, not a subnet mask, but a wildcard mask of 0.0.0.255, and we'll assume that PCs A and B are using a 24-bit subnet mask, so this would be an appropriate wildcard mask. And we said that PCB should be allowed, so now we're following up that first access list entry with a permit statement saying we're going to permit the host IP address of PCB. We take that access list, we go into Fast Ethernet 0/0, and we're applying it in the inbound direction, but PCB is not getting through. In our previous scenario, we had neglected to enter a permit statement for PCB, and as a result, PCB could not reach the servers, but here we have given a permit statement, and we're still not able to reach the servers. Again, you might want to pause the video unless you already know what's going on, and hypothesize what the issue is here, and when you're ready, you can resume the video and we'll discuss the solution. As you were thinking about this scenario, the access control list characteristic that I wanted you to think about as you were going through this exercise was that ACLs are processed top-down. And as soon as we hit that first ACE, that first access control entry that's denying all IP addresses in the 10.1.1.0/24 subnet, that entry is blocking traffic from PCs A and B. So it really doesn't matter that the next entry says we're going to permit PCB because the first entry already denied it. And since we're processing things top down, we never even consider that second statement. And as a result, PCB is blocked. If we reversed those two access control entries, that actually would meet our goal. Let's take a look at another scenario. In this scenario, the goal is that PCA should be able to connect to server 1 via TFTP, and PCB should be able to connect to server 2 via FTP. But the symptom is PCA is unable to reach the TFTP server. Let's take a look at our access control list and see if we can figure out what is going on. Our first statement is access-list 101, so we know we're working with an extended ACL this time because the number is in the range of 100 through 199, and we're saying permit TCP host, and we give the IP address of PCA and the destination. Remember, with an extended access list, we can specify a destination, and the destination is a host with the IP address of server 1, and because we're wanting to allow TFTP traffic to go to server 1, we're saying EQ69. 69 is the TFTP port number. We have a similar access list entry for PCB trying to connect to server 2 via FTP. We're permitting TCP traffic from PCB's IP address to server 2's IP address using the FTP protocol. And we're taking this extended access list of 101, going into Fast Ethernet 0/0 and applying the access list in the incoming direction. And this is allowing PCB to reach server 2 using FTP, but a nearly identical configuration is not working for PCA. You might find this one a little bit trickier than our previous two scenarios. You might want to pause the video and resume when you're ready for the answer. Something very subtle is going on in this exercise, and it's something you learned way back early on in the video series. This is valuable information for the real world. Not only should we realize that TFTP uses port 69, but it's not a TCP port, it's a UDP port. And as a result, that TFTP traffic from PCA to server 1, it is not matched and therefore not permitted by that first entry because it's UDP traffic instead of TCP. The fix to this configuration is to replace TCP in that first entry with UDP. Then the TFTP traffic would flow through. Let's take a look at our final troubleshooting exercise. In exercise number 4, we've got a goal that says allow PCA to reach server 1 and server 2, but prevent PCB from reaching either server. And the symptom is neither PC can reach server 1 nor server 2. Let's take a look at our access control list. The first entry says we want to permit the host IP address of PCA to reach the 192.168.1.0/24 network. And even though we would not necessarily need a deny statement, because we have that deny any statement that's implicit at the bottom of our access control lists, we do have a deny statement here, and we're denying all IP traffic from the IP address of PCB going to the 192.168.1.0/24 network. So far, that's all looking good. We're going into interface 0/1, and we're applying the access list in the inbound direction. For the final time, you might want to pause the video, ponder what's going on, and come back for the solution. Again, we had something very subtle going on in this scenario. Did you notice the interface was Fast Ethernet 0/1? We had been using Fast Ethernet 0/0 in our previous scenarios, and now it's Fast Ethernet 0/1. That's not to say we could not use that interface. We absolutely could apply an access control list to that interface. In fact, this access list would work beautifully, except it's applied in the wrong direction for that interface. Notice it's being applied in the inbound direction. That means coming in from the 192.168.1.0/24 network. If we had applied that access list outbound, going out of router R1, going toward the right of the screen, then this would have worked. And you might wonder at this point, if there is no outbound ACL applied to Fast Ethernet 0/1, then it seems like all traffic should go out of router R1. Why are things not working? Well, actually, traffic does go out of router R1. Our packets actually are getting to the servers. But the symptom from our perspective is that we're not reaching the servers because the return traffic is not getting through. As return traffic is coming back in from servers 1 and 2, we're running into that inbound access control list as we're coming into Fast Ethernet 0/1. And our source addresses are from the 192.168.1.0/24 network. In other words, packets coming in to router R1 on Fast Ethernet 0/1, there's no way that they're going to match that permit statement that we have. We're coming from a different network. This means that we're not permitting anything, and therefore the implicit deny any is going to be dropping everything. Packets are actually getting from PCs A and B to servers 1 and 2, but the return traffic is not allowed to come back into R1, and as a result, the symptom appears to be that these PCs are not able to reach these servers. A couple of easy ways to fix this. We could apply that access list in the inbound direction to the other interface, Fast Ethernet 0/0, or we could still apply it to Fast Ethernet 0/1, but we should apply it in the outbound direction.